Our first speaker in this section is Lisa Schleicher. She'll be talking on constructing a probabilistic seismic hazard analysis framework for the moon. Take it away, Lisa.
Hello, everyone. I'm really excited for this opportunity to share with you some work we've been doing to develop a probabilistic seismic hazard analysis for the moon. One of the inspirations for this study has been the Artemis mission and the idea that we might be going back to the lunar surface, perhaps creating a more sustainable permanent structure of some sort, whether it have a nuclear power source or other power source or other life-sustaining features. We'd want to ensure that seismic hazards are reliably characterized and then mitigated for those important features that would sustain us. So it's kind of what's motivated us. And this picture you see here, the components of a PSHA, or probabilistic seismic hazard analysis. So we have our seismic source, so three main components: the seismic source model, so where are our faults, how far away are they from our site of interest, how big of events can they produce, our ground motion model, or ground motion attenuation relationships. So how do we expect the ground motions to travel from the source through the crust to our site? And then the site effect is the third component, or the site response model. How do soils or materials in the near surface amplify or de-amplify ground motions at our site? So these are the three components you can kind of have in your mind as we think about PSHA for the moon. On the left here, I have kind of another schematic showing the components of a PSHA. So now looking at the seismic source model in map view, down on our site of interest, you can see the site. We want to know how far away, and then what is the recurrence rate, what magnitude, and what recurrence do we have on those sources? How active are these sources? So those are the main pieces of a seismic source model. And then we have our ground motion model.
Sorry to interrupt. Can you hit your swap displays at the top of your screen?
Oh,
we're seeing your presentation mode. That's fine. We could follow it pretty easy.
Sorry about that. Thanks. Is that better? Is that working now?
I haven't noticed it swap yet. Oh, there it goes. Okay, I'm good. Yep.
Oh, okay. So sorry about that. For the ground motion model, you can imagine you have distance versus your peak ground acceleration. So mathematically, we want to have a way to characterize how does the ground motion attenuate through the crust. And as you can imagine, the closer you are to the source, the greater the ground motions would be, and they'd be lower further away. And you'd have different ground motions for different magnitude events, so different relationships. And we need a way to mathematically characterize those. And once you have your seismic source model and your ground motion model, we can combine those to get what we call seismic hazard curves. So this is for a certain probability of exceedance, or you can think of this as like your risk level that you're interested in. What would the acceleration be? And we actually create these curves for a variety of frequencies. So one curve for every frequency we're interested in engineering, which on Earth tends to be from 0.1 to 100 hertz. These are the ground motions that most structures attenuate at. And so we would want to look at that hazard and compare it to our building design or structure design that we're interested in, with the idea that the structure should bound that hazard so we can mitigate against any potential events. And so something we've had in our minds while thinking about this project is what would it take to make a seismic hazard for the moon, similar to the USGS National Seismic Hazard Map. So here's an example for the US for the 2% 50-year probability. And can we make something like this for the moon to kind of get an idea of what our hazard is in particular geographic regions on the moon we might be interested in going to and exploring further. So what do we know about the moon? What do we know about seismic hazard on the moon? Well, we're very lucky to have the LRO spacecraft, which has given us a vast wealth of high resolution imagery and altimetry data, which has allowed us to map at a global scale where are the faults. These are the lobate scarp thrust faults, which we think have evidence to be potentially active. So, so anytime you have a recently active fault, that gets considered in your seismic hazard analysis with the idea that it could be active in the future, or at least these faults give us an idea about how is the moon currently deforming. So here on this map, you can also see some of the shallow moonquakes, and some of which have been associated with some of these faults. So we have a great fault map, global scale fault map for the moon. Thanks to the Apollo missions, we also have a variety of ground motion records from the Apollo era timeframe, where we can start to develop magnitude recurrence relationships. So we could start to get a handle on how seismically active is the moon, or at least we have some data for doing that. On the right here, you can see 3 different relationships we've been exploring. So depending on how you assign the moment magnitude to those events, you'll get different relationships. So we're exploring these amongst others as a way to kind of capture the magnitude recurrence rate on the moon. And then we take these models, both where are the faults and how active is the seismicity, and kind of can combine them to create our seismic source model. And so here we're just showing some ideas we've been exploring to do a gridded approach of the hazard of the sources on the moon of seismicity. So if we take the total fault length per gridded area across the globe, we can get an idea of productivity. So you could imagine the more faults you have, the more cumulative length you would have. So kind of an interpretation would be is maybe that part of the moon is more productive and more tectonically capable of producing seismicity. Whereas on the right, we have magnitude potential. So here we just use average fault length as a proxy, or the idea that the average length of your fault could correlate to your magnitude potential. So how big of events could you have? So these would be potential inputs to our seismic source model. For the ground motion model, we have a great starting point for that. Here's a shake map for the Mandelscomb Scarp for a magnitude 6.3 event. You can see, of course, close into the scarp, you have the greatest ground motion. So in map view on the left and ground motion view on the right. So you kind of have our attenuation, our modeled attenuation relationship here. Whereas then closer to the fault, you have greater ground motions, and then out at distances it decreases. But this is just for one magnitude of interest. For a hypothetical situation, for a PSHA, we would want to include a range of magnitudes and a range of sizes of faults and such in our hazard. So something we've started to explore is using machine learning. So since we only have some records to guide us on the attenuation on the moon, we thought that creating some synthetic waveforms might be a way to kind of widen our available data set for modeling our ground motion on the moon. So here you can see distance versus the ground motion. These are for different azimuths, on the moon, or different kind of wavelength paths that you might expect. And then you can see there's sheets in there. So the top one are the greater magnitude events, and then going down in magnitude. So the idea is we create this suite of data, and we could use something like this to create a ground motion prediction equation for the moon. So something preliminary that we're exploring right now. And then for the site response model here, what we have are some information on the near surface. So thanks to Apollo 16 astronauts, they put out a geophone line, and we're able to collect some data in the near surface. And from this, we have some constraints on what's the depth to bedrock, from what's the thickness of the regolith. This is an important input into site response modeling. And then from that, we can model what amplification from the near surface materials might we expect. And this is an important component of a PSHA. And so finally, kind of our next step, this is sort of a work in progress, is we're going to combine our seismic source, ground motion, and site response models to create site-specific hazard curves. And we think we'll focus on the South Polar region because of the interest in the South Pole due to the potential for water ice in these permanently shadowed regions. It might be a place we might go. So we could create hazard curves there to get an idea of what the hazard would be in the South Pole. And something interesting, we know there are lobate scarps near some of these permanently shadowed regions that we might go to. So here's one here in this picture you can see. We've also started to think about topographic amplification. So if you put a facility on the crater rim, how is that going to amplify ground motions? So there's some unique considerations. There's a lot of craters that are filled in, similar to the basins on Earth where you have surface wave edge effects. Is that something that might control the hazard on the moon? So these are things we're starting to think about. Also thinking about if we're going to the moon, if astronauts are going to be there, are there things they can do? Putting out seismometers would allow us to get some information on the site in the South Polar region, which may be different than the Apollo landing sites. That would be important for seismic hazard. Geophone arrays, we might be able to image faults and things like their dip direction, especially if you're close to the fault, would all control your hazards. So there's activities that we've been brainstorming about that could be done to kind of constrain the PSHA uncertainty. But for this, we're just trying to get a starting point and starting to think about the concept and these ideas. And so we're really excited to present this to this community and welcoming any feedback anyone has as we continue to develop this. And that's what
Okay.
I have. Thank you.
All right. Thank you, Lisa. We didn't leave time for questions, but if you do have your questions, write them down so you don't forget them. And we will entertain them during the discussion period. So I'll remind speakers now to stick around. You might get questions for the discussion period. So please don't leave the session. All right. Thank you, Lisa.